In this video, we are solving LeetCode problem 167 to sum 2 input array sorted. We are given a sorted array called numbers and an integer called target. We need to find two different elements whose sum is equal to the target and return their positions. There are three important details. First, the array is already sorted. Second, the answer must use one base indexing. Third, we must use only constant extra space. Let us understand how the sorted order helps us solve this efficiently. Consider this example. So numbers equals 2, 7, 11, 15 and target equals 9. The numbers 2 and 7 add up to 9. Their array indices are 0 and 1. However, the problem uses one base indexing. So we return 1, 2. The problem guarantees that exactly one valid solution exists. We are also not allowed to use the same element twice. Now let's start with the brute force approach. The most direct approach is to check every possible pair. We can select one number and compare it with every number after it. For every pair, we calculate numbers I plus numbers j. So for every pair, go through all the pairs. For every pair, calculate this. If the sum equals the target, we return the two indices. This solution works, but time complexity is O n square. And constraints, if you look at it, then it is sufficiently great. So we need to use an optimal approach. We could also use a hash map like in the original two-sum problem. However, a hash map requires O and extra space. The problem specifically asks us to use constant extra space. Fortunately, the array is sorted, which allows us to use the two-pointer technique. So the thing is, what about hash map approach? It uses O and extra space. But the problem asks for O1 space. So we can't use that. So let's come to two-pointer approach. We could not use it that time because at that time the array was not sorted, but this time array is sorted. So we place one pointer at the beginning of the array and another pointer at the end. So the two pointers are left and right. Left at the beginning and right at the end. So we initialize with these values. The left pointer represents the smallest available number and right pointer represents the largest available number. We calculate their sum. Now there are three possibilities. Calculate the sum of left and right. Three possibilities are there. First is that the sum equals the target. So we have found the answer, we can return the left and right. Second case is sum is smaller than the target. So we need a larger sum. Because the array is sorted, moving the left pointer towards the right gives us a larger or equal number. Therefore, we increment left. And third possibility is the sum is greater than the target. We need a smaller sum, so move the right pointer towards the left uh, because it will give us a smaller or equal number. Therefore, we decrement right. So we continue until we find the required pair. So why does this work? Suppose the sum. So let me explain once again. So in this case, we found the answer. While in the case when sum is smaller than target, move left towards right. And in the third case, when the sum is greater than the target, we move right towards the left. So why does this work? Suppose parent sum is smaller than the target. The number at the right point is already the largest number available in the current range. If the smallest number cannot form the target with this largest number, it cannot form the target with any smaller number either. Therefore, we can safely remove the current left number from consideration. Similarly, suppose the current sum is greater than the target. The number at the left pointer is already the smallest number available. If the largest number produces a sum that is too large, even with the smallest number, it will also produce a sum that is too large with every larger number. Therefore, we can safely move the right pointer. This is possible only because the array is sorted. Now, the algorithm. Let us come up with the algorithm. First, we set left to 0. Then we set right to the last index. Then we calculate the sum of elements at left and right. Then number 4 is if the sum equals the target, return their one based positions. So what is one based? For example, the array here, the index of 2 is 0, 7 is 1, 11 is 2, and 15 is 3. So one based indexing means we will say the index of 2 is 1, 7 is 2, 11 is 2, 3, and 15 is 4. So this is the one based indexing. We use zero based indexing by default, but this problem says to use one based positions. Then fifth step is if the sum is smaller than target, increment left. And if the sum is greater than target, then decrement right. And repeat until the answer is found. So this is a simple algorithm. Now let us write its pseudocode. All these things becomes obvious by practicing it. Now we initialize left equal to 0, right equals length of numbers minus 1. Then start the loop while left is less than right. Current sum equals number on left and plus number on right. Then the first case, if it is equal to target, then we return the one based index. And if it is smaller than the target, then we move left one step forward. And finally, if it is greater than target, then we move right one step backward. We add 1 to both indices because the problem expects one based indexing. Now let us write the Python code. So we initialize left and right and start the loop. Current sum, we calculate the current sum, then check the condition. If it is equal to target, then we return the one based index. And if it is less than target, we increment the left by 1. And otherwise we decrement the right by 1. Finally, if, in some case, for example, when the array is empty or anything, then we return the empty array if nothing is found. Also the final empty, because it is mentioned in the question that there will obviously be an answer to this to all the test cases, and also there is no empty numbers. We are returning this empty array because we want to satisfy this thing list, that the function should return a list in the end. So that's why we need to return an empty list. According to the problem statement, exactly one solution always exists. So the loop will return the correct pair. So we begin by creating the 2 pointers, left equal to 0, right equals then numbers minus 1. The left pointer starts at the first element, the right pointer starts at the last element. Next we continue while the 2 pointers refer to different elements, while left less than right. The condition also ensures that we never use the same element twice. Inside the loop, we calculate the current sum. Current sum equals numbers left plus numbers on right. If the sum is equal to the target, we return the positions. That is return left plus 1, comma right plus 1. We add 1 because the problem uses 1 based indexing. If the sum is too small, we do left plus equals 1. We move towards a larger number. Otherwise, the sum is too large, we do right minus 1, minus equals 1. We move towards the smaller number. Now let us do a dry run to understand it more deeply and more clearly. So our numbers equals 2, 3, 4 and target equals 6. So initially left equal to 0 and right equals 2. And the values are numbers left equals 2 and numbers right equals 4. Their sum is 2 plus 4 equals 6. The sum equals the target. The zero base indices are 0 and 2. So we return 1 comma 3, the one base index, or let me write answer equals 1 comma 3. Now let's do one more dry run. So this time numbers equals 1 comma 2 comma 4 comma 6 comma 10 and target equals 8. So initially left equal to 0 and right equals 4. And the sum is 1 plus 10 equals 11. So these two are the starting number and their sum is 11. 11 is greater than 8. 11 is greater than target, that is 8. So left will become equal to 1. Now sum equals 2 plus, so it is greater than target, so right will be decrease. Right equals 3. So sum will now become 1 plus 6 equals 7. So 7 is less than target, less than 8. Therefore left will become equals 1. Now sum equals 2 plus 6 equals 8 equals target. Therefore it will return answer equals left plus 1 comma right plus 1. So what was our left? That was equal to, so answer will be 2, comma 4. As you can see, this and this sum up to a target. So we are getting the correct answer. Now let us try to run the code. Let us first test it with simple test cases. Now let us submit it. Okay, so all the test cases are passed. Now finally let us discuss its time complexity. So because we are scanning the array, every element is processed at most one times. So each pointer moves only in one direction. The left pointer can move at most n times, and the right pointer can also move at most n times. Therefore, time complexity is O(n). We only use pointer variables and one variable for the sum. Therefore, the extra space complexity is simply constant O(1). This satisfies the constant extra space requirement. Now let us discuss some common mistakes. So first mistake is returning zero-based indices. It is clearly mentioned in the problem that it expects one-based positions. So don't return left comma right, but left plus one comma right plus one. Second is moving the wrong pointer. When the sum is too small, move left forward. When the sum is too large, move right backward. Then third mistake is using left less than equal to right. So this is wrong. Using left less than equal to right may allow both pointers to reference the same element. So use while left less than right. Then fourth mistake is ignoring the sorted array condition. The two pointers movement is correct because the array is sorted. The same logic cannot be directly applied to an unsorted array. Then fifth mistake is using unnecessary extra space. A hash map can solve to some, but this problem specifically requires constant extra space. The sorted order makes the hash map unnecessary. So finally, let's recap. In this problem, the most important clue was that the input array was sorted. We placed one pointer at the smallest number and another at the largest number. If their sum was too small, we move the left pointer. If their sum was too large, we move the right pointer. If their sum matched the target, we return their one-base position. The final complexity was O(n) in time and O(1) in space. This is a classic example of how sorted data can convert a pair searching problem from a quadratic time into linear time or two-pointer solution.